Good morning. My name is Robert Ellis, the Old Master Coach. Today we're going to look at Pythagoras Theorem. Pythagoras didn't invent this theorem. In fact, he was known over 1,000 years before he was born. But the theorem is attributed to his name mainly because he wrote a textbook and he included this theorem in his textbook. Now, what a lot of people know about Pythagoras' theorem is that the area of the square on the hypotenuse of any right-angled triangle, this area here is equal to the sum of the squares on the other two sides. Now, many parents and many people who have been through school and left school for many years still remember this as maybe the only thing they can remember about mathematics when they were at school. That shows you how important it is, because Pythagoras' theorem is a very, very useful tool in building and many other applications. Today I'm going to look at some of the other things that Pythagoras knew about the right-angled triangle that not very many people know. Now, for the sake of argument, we're only going to consider triangles where the three sides are relatively prime. Now, what I mean by this, 3, 4, 5 is a right-angled triangle. The three sides are relatively prime because the numbers 3, 4 and 5 don't have a common factor except 1. If we look at 6, 8, 10, that's the same triangle where the numbers have all been multiplied by 2. So whatever applies to the 3, 4, 5 triangle will definitely apply to the 6, 8, 10 triangle and the 9, 15, 12 triangle. So we're only going to look at triangles where the sides are relatively prime. Now, what Pythagoras came up with, that the product of those three sides, A multiplied by B multiplied by C, is always divisible by 60. When you think of some Pythagorean triads, 8, 15, 17, 8 15s is 120, that's divisible by 60. 20, 21, 29, 21's got a factor of 3, 20's got a factor of 4 and 5, 3 times 20 is 60, that's divisible by 60. And that applies to every right-angled triangle where the sides are whole numbers. I'm going to prove that today in a very simple proof, far more elegant I feel than the geometrical proof that Pythagoras used to prove this thousands of years ago. And I'm going to do this by using what we call modular arithmetic. Now, in our base system, we consider our numbers base 10. When we have a 0, we're always divisible by the base 10. 60 is divisible by 10, 100 is divisible by 10, 40 is divisible by 10. In base 3 systems, any number that ends in a 0 is divisible by 3. In a base 5 system, any number that ends in a 5 is divisible by 5. Now we're going to look at the right-angled triangle ABC, and we're going to look at a squared plus b squared plus c squared in terms of those the three bases, 3, 4 and 5. Now in mod 4, we can say every number is either even, and we can represent it by 2k, or odd, which we can represent by 2k plus 1. If we square an even number, then we square 2k, we get 4k squared, that's divisible by 4. If we square 2k plus 1, we get 4k squared plus 4k, they're both divisible by 4, and 1 remainder. So we say in mod 4, every square number ends in 0, means it's divisible by 4, or it ends in 1. In base 3, we can partition the numbers as 3k, 3k plus 1, 3k plus 2, and you can do that as a little exercise. You square this, it's divisible by 3. You square this, your remainder is 1. You square this, your remainder is 1 after you take out the factor of 3. So all square numbers in mod 3 end in a 0 or 1. Now I can leave it to you as an exercise. which if you're interested, it's very simple to do. The mod 5 numbers are 5k, 5k plus 1, 5k plus 2, 5k plus 3, 5k plus 4. And if we square all those and take out the factor of 5, we see that all square numbers in mod 5 are divisible by 1 or 4. Now let's put those square numbers, the remainders of these mod numbers, into our squares. If we put a 1 in C, and we're looking at base 3 and 4 because they're the same, if we put a 1 in here, what numbers can we put in A and B? Well, these two numbers, these square numbers, have to add up to a square number of 1. So if we put a 0 here, putting a 0 there means that A is divisible by 3 if we're looking at base 3, and if we're looking at base 4, then A is divisible by 4. If we put a 0 here, we have to put a 1 there, and so we have the fact 0 plus 1 equals 1. Supposing we didn't put the 1 in C, we put a 0 in C, and we're using now bases 3 and 4. So we have a look. If we put a 0 in C and we put a 1 in A, then we can't have 1 plus 1 equals 0, because 1 plus 1 equals 2, or we can't have, and we don't have a 2 in base 3 or 4, so by putting a 0 here, the only way we can get a 0 here is to have a 0 in A and a 0 in B. Now if we have zeros in all three, that contradicts what we said to start with, because all three then have a common factor. So it's impossible to have three sides of a right-angled triangle which are relatively prime such that the hypotenuse is divisible by either 3 or 4. So the only case we can have is that the hypotenuse is never divisible by 3 and 4, and always one of the sides, A and B, is divisible by 3, and one of the sides, A or B, is divisible by 4. Hence, the product of AB has to be divisible by 12. Now all we have to do to solve our problem to show that the three sides are divisible by 60 is to find out if one of the sides is indeed divisible by 5. And to do that, we go to mod 5. Let's just remove these numbers and start thinking in mod 5. In mod 5, we can have the hypotenuse ending in a 4. So let's do that. If that ends in a 4, the only way we can combine these two of these to make up a 4 is by adding 0 and 4. Putting a 0 here and a 4 there. Note A and B are interchanged, so it doesn't matter which one we put the 0 in. Then this number here, A, has to be divisible by 5. So putting a 4 in the hypotenuse, that means that one of the small sides is divisible by 5. Let's go the other way, let's put a 1 in the hypotenuse. If we put a 1 in the hypotenuse, the only way we can add two of these to get a 1 is by 0 and 1. And again, that means if we put a 1 in here, then one of these two sides is divisible by 5. And since we got these two sides are divisible by 3 and 4, 3, 4 and 5, that means the product of the three sides is divisible by 60. The only alternative we haven't looked at, we didn't put a 0 in here. By putting a 0 in there, the only way we can get a 0 in there is by putting a 0, a 1 here and a 4 here. That gives us 0 because 4 plus 1 is 5. Or the trivial case, which we're not considering, is putting 0 and 0. We're not considering 0, 0, 0. So by putting a 0 here, it means already it's divisible by 5, and we can have these two being numbers which are mod 1 in mod 5 and 4 in mod 5. So hence, any right-angled triangle where the sides are all integers, then the product of the three sides is always divisible by 60, and the product of the two sides, including the right angle, is always divisible by 12. Now, that little bit of information, you may say, well, what's the point of it? Well, mathematics seems to have a habit of when we have something which we think is not important, suddenly down the track takes on monumental importance. Or maybe this will, I don't know, but it's certainly an interesting fact to know. And it was known, as I said, many, many years ago, but the proof was done using geometry. I've now done the proof in a simple way that even very young high school students should be able to follow. There is one other thing, conjecture, that I've found, not been able to prove or disprove or to find an example that disproves it, but I've found that in every right-angled triangle I've looked at, where the three sides are integers, then the hypotenuse is either a prime number, like 17 or 29 or 41, or else it's a number which is divisible by 5 times a prime number. So if we have the triangle 33, 56, 65, which is a Pythagorean triad, I'll write those on the board so you can keep them in your mind. 33, 56, 65, which is 5 times 13, which is 5 times a prime number. Or if we have a look at 20, 99, 101, that's a prime number. So it's either going to be a prime number or a number which has a factor of 5, which is the case when we put a 0 over here, and that number has a factor of 5 and the other factor is a prime number. I cannot prove that. I cannot find a counterexample to it. If you do know counterexamples, those people really good with computers probably can. Please let me know, because I would like to know where the first counterexample exists. My name is Robert Ollis, the old master coach from Master Coaching. If you want more information about mathematics or anything to do with numbers, go to our website, www.mastercoachingaustralia.com. There are many other videos that you may enjoy. Take care, enjoy the journey.